The ground state energy of a particle of mass m in an infinite potential well is E naught. It changes to E naught into 1 plus alpha into 10 raised to minus 3 when there is a small potential bump of height V naught is equal to pi square h cross square divided by 50 ml square, and with A is equal to L divided by 100. The value of alpha is dash. In this question, they have taken a particle of mass m in an infinite potential well and whose ground state energy is E naught, and the energy level, ground state energy level, changes to E naught 1 plus alpha into 10 raised to minus 3 when there is a small potential bump. The diagram is given. When there is a small potential bump, the energy value rises to E naught alpha into 10 raised to minus 3. So they have asked us to find what is the value of this alpha. If we take this square well potential without any perturbation, we can get an eigenvalue E of n is equal to n square pi square h cross square divided by 2m L square. And the eigenfunctions I of n is equal to root 2 divided by L sine n pi x by L, and where n goes from 1, 2, 3 and so on. First, we will find the first order correction for the ground state n is equal to 1. That is E is equal to integral from a to b root of 2 divided by L sine pi x divided by L V naught root 2 divided by L sine pi x by L into dx. This constant terms can be taken out. So we will be getting 2 V naught by L integral from a to b. 2 sine term is there. So we will be getting sine square pi x divided by L into dx. We have to find what is the value of A and B, that is the limits. This is the given potential well. The total length is A and the potential bump width is A. So this point A corresponds to the position L divided by 2 minus A by 2, and B corresponds to L by 2 plus A divided by 2 position. Therefore, we can apply the limit. Now we have to find a way to integrate the sine square term. Sin squared theta can be written as 1 minus cos 2 theta divided by 2. Therefore, this term can be simplified as 1 minus cos 2 pi x divided by L divided by L divided by 2. So, this 2 can be taken outside. So, it will cancel off with this 2. We will be getting V naught divided by L integral a to b 1 minus cos 2 pi x divided by L into dx. By integrating this term, we will be getting x minus sine 2 pi x by L divided by 2 pi divided by L. Now apply the limit and simplifying this, we will be getting V naught L into A plus L by pi sine A pi divided by L. In the question, they have given the value of A as L divided by 100. Now substitute in this expression of E. We will be getting V naught by L into, here A term is there, so we can substitute L by 100 plus L by pi into sine of, here another A is there. We substitute L by 100, we will be getting pi by 100 as simplified 1. Now sine of 180 by 100 value is 0.0314. This is nothing but pi divided by 100, that is pi value is 3.14. Therefore, we will be getting pi divided by 100, and simplifying it, we will be getting the value of E as 20 into V naught into 10 raised to minus 3. Now we have to find what is the value of V naught in terms of E naught. In the question, they have given the V naught value, and for the ground state of unperturbed system, E naught value is pi square h cross square 2m L square. So by dividing these two terms, we will be getting V naught is equal to E naught divided by 25. We have to substitute the value of V naught in here. E is equal to 20 into V naught into 10 raised to minus 3. We will be getting 20 by 25 E naught into 10 raised to minus 3. By comparing this with the given ground state perturbation energy, we will be getting alpha value as 0.8. Question: an atom in its singlet state is subjected to a magnetic field. The Zeeman splitting of its 650 nanometer spectral line is 0.03 nanometer. The magnetic field is dash Tesla. So in this question, they have taken an atom in a singlet state and they are subjected to a magnetic field BZ. Okay, and the splitting happens in the magnetic field. And they have asked us to find what is the value of this magnetic field. We know that the interaction energy of the atom delta E is equal to mu B into Bz. The value of mu B is known, that is minus Heg divided by 4 pi m into Bz. In the question, they have not given the value of delta E, but they have given the value of lambda and also delta lambda. We have to write delta E in terms of lambda and delta lambda. We know that energy E is equal to Hc divided by lambda. By differentiating it, we will be getting delta E is equal to minus Hc divided by lambda square into delta lambda. We can substitute the value of delta lambda here. Okay, then when simplifying it, we will be getting the value of magnetic field Bz, that is equal to 4 pi mc delta lambda divided by lambda square E into G. In the question, already they have given the value of E, mass of the electron and the velocity of the light, and lambda value is 650 nanometer and delta lambda is 0.03 nanometer. For a singlet state, the value of G is 1. By substituting the values, we will be getting Bz value as 1.52 Tesla. Question: the quantum effect in an ideal gas becomes important below a certain temperature Tq when de Broglie wavelength corresponding to the root mean square thermal speed becomes equal to the interatomic separation. For such a gas of atoms of mass 2 into 10 raised to minus 26 kg and number density 6.4 into 10 raised to 25 per meter cube, the Tq is equal to dash into 10 raised to minus 3 Kelvin. So in this question, they have taken an ideal gas, and for the ideal gas below a certain temperature of Tq, quantum effect has become very important, and below that temperature they have said de Broglie wavelength lambda is equal to A, that is interatomic separation, and they have asked us to find what is this temperature below which the quantum effect becomes very important. First, we will write that de Broglie wavelength lambda is equal to h divided by root of 2me. Here we have to find what is the value of E. According to equipartition theorem, we can write E value as 3 divided by kBt. By simplifying it, cancelling this 2 and this 2, we will be getting h divided by 3m kBt. So in the question they have given when temperature is equal to Tq, lambda value is equal to interatomic separation. Now instead of lambda we can write A, and for T we can write Tq. So the expression will become A is equal to h divided by root of 3m kb into Tq. So interatomic separation is related to number density by 1 divided by rho power 1 by 3. So we can, instead of A, we can write 1 divided by rho power 1 by 3 is equal to h divided by root of 3m kb Tq. So by rearranging this expression, we can write Tq is equal to h square rho square the whole power 1 by 3 divided by 3m kb. So all these values are known. By substituting it, here we will be getting the whole power 2 by 3 is missing. So by evaluating it, we will be getting Tq as 84.15 the whole power minus 3 Kelvin. In the description box, you can find the link for GATE Physics 2019 and 2020 solution. Please share and subscribe the channel. If you have any queries, write in the comment section.